Our first topic is soil water retention and potential and soil moisture constants. For that, first we have to know the how water is retained in soil. Basically, so the two main forces are there, as I told yesterday also, that cohesion and adhesion forces of soil are the main responsible factors for adhesion, for retention of water by soil. What are those? Again, I am telling that cohesion means means same. That is when a water molecules attract water molecule, that is cohesion, and when a soil particle attracts water, that is adhesion. For it has been written here also. One is the attraction of molecules for each other, that is cohesion, and the other is the attraction of water molecules for the solid phase of the soil, that is soil and water particles interact each other, and that is adhesion force. By these two forces act together and holds water in the soil. Next is surface tension. Due to surface tension of water, the soil particles attract the soil or the soil water, and it shrinks it snatches down the water surface towards itself, like just for downward movement, and it causes a surface tension on the upper layer of the water, causing the water to hold in the soil pores. Next is polarity or dipole character of water. Water has two hydrogen atoms and one oxygen atom. So the H plus ion has positive charge, and oxygen atom has a negative charge here. So what happens when a clay particle is present? Clay has a negative charge and hydrogen has a net positive charge. In that case, the hydrogen molecules are attracted by the clay particles, and it retains the water molecule in the soil. In this way, soil holds water. And next is soil water potential. Coming to the potential of anything is defined as the power or the capacity to work. In the same way, the potential of soil water can be defined as the energy of water, that is pure water, with no external forces acting on it, and when it is present at a atmospheric pressure and at a given temperature and at a given height from the reference point. The potential energy is measured as by multiplying its mass, gravitational force, and the height from the reference level at a particular temperature and atmospheric pressure. In that way, the potential of soil water can be calculated. Next, in defining the soil water potential, there is a true definition given by USDA is total soil water potential is defined as the amount of water that per unit quantity of pure water that must be done by external forces to reversibly and isothermally and infinitesimal quantity of water from from the standard state of the soil to the soil at the point under consideration. What does it mean? That soil water potential, the work done by any external forces to transfer reversibly, that is the amount of work done to take water from point A to point B and point B to point A will be same, and isothermally, that is the temperature during this transfer will not be changed. That is an infinitesimal amount. That means very small amount of water is being transferred to the standard state, from the standard state, that is from pure water to the pure water, a pool of pure water, and to the soil to any point where we can transfer it. Now, soil water potential can be measured or expressed in these units are very important for exam purpose. They are like soil water potential is measured in 3 units: per unit mass, per unit volume, and per unit weight. So for per unit mass, the unit is Newton meter per kg, and per unit volume the unit is Newton per meter square, and per unit weight the unit is centimeter or meter. These are some of the conversion that is you very frequently asked in GRF SRF question. Now, soil water potential is composed of 4 components, that is metric potential or capillary potential, solute or osmotic potential, pressure potential, and gravitational potential. Now, let us come to discuss one by one. First is gravitational potential. What is gravitational potential? Gravitational potential is the potential of water, soil water at each point is determined by the elevation of the point related to some arbitrary reference level. For example, if we consider a soil profile here, and the surface of the soil we consider as reference level, then at a height of 1 meter, at a depth of 1 meter, the gravitational potential is the density of water, that is rho, the h, that is 1 meter height, and g is gravitational acceleration, that is 9.181 meters per second square. So it comes around minus 9.81 kilopascal. It is minus because the height we are considering is below the reference level. If it was above the reference level, it was plus 9.81 kilopascal. Similarly, for metric potential, it is associated, metric is associated with soil matrix. So from the name, it can be understood that metric potential result from the forces associated with the colloidal metric and include forces associated with adsorption and capillary, that we understood earlier, the forces of adhesion, cohesion, and surface tension. These forces attract and bind water in the soil and lower its potential energy below that of bulk water, because pure water has zero energy, no energy, that we consider it as a zero energy. And if it is adsorbed on the surface, so its capacity to move from the soil particles is decreased. That means its energy is reduced. So metric potential is expressed as negative term, and osmotic potential is present due to the arises due to the presence of salts or any solutes in the soil water. Like for example, if you add any salt, it has cationic part and anionic part. So cation and water is a dipole, as I told earlier. It has oxygen as negative part and hydrogen in its positive part. So if you add any cation and anion, sodium, for example, sodium chloride, we have added sodium chloride. So look at here, the sodium part is attracting the oxygen part, that is sodium is a cation, it is attracting the oxygen part of water. Similarly, if we in the chlorine part, that is, so if we add sodium chloride, the anion part will be chlorine. In that case, the chlorine part will attract the H plus. In that way, it will reduce the capacity of soil water to move from one place to another. In that way, soil it will the osmotic potential will reduce its movement. Here it has been written. Now one question is asked generally, that hydraulic head in soil, that hydraulic head is generally the total head, which is, if we consider this as groundwater level, this is total hydraulic head, and it is the datum level, that is reference level, and pressure, the pressure head plus elevation head, total comes to the gravitational hydraulic head, that is gravitational head plus soil water pressure head is called hydraulic head. How can we measure this potential? First, we can measure this potential using a simple tensiometer up to the range of 0.8 bar, 0 to 0.8 bar. For other ranges, we use different techniques, like for low section, like 100 centimeter water, 100 centimeter, 0 to 100 centimeter, that is 100 bar, 1 bar, we can use sintered glass balloon or Hens jumps technique or tensor table technique, or sandbox technique, or plastic membrane technique. For medium section, that is 100 to 1000 centimeter of water, we can use, that is pressure plate extractor and pressure membrane method. For more higher section, it is 1000 to 20,000 centimeter water, we use pressure plate extractor and pressure membrane extractor. For very high section, we use vapor pressure equilibrium using vacuum desiccator. These are the methodologies used for measuring soil water potential in different ranges. Now, soil water constants. Soil water is present in soil in different suction and as well as different forces. If we saturate a water by irrigation and we allow it to drain for under the force of gravity, after 2 to 3 days, the soil will still hold some amount of water. That is called the soil field capacity of soil water. So it is defined as the capacity of the soil to retain water against the downward pull of the gravity. At this stage, only micropores or capillary pores are filled with water, and plant can absorb this water. And this is very important, that the field capacity water is held with a force of 1/3 atmosphere or 1/3 bar. That is 0.33 bar. Next is wilting coefficient. The wilting coefficient is as the moisture content falls, a point is reached when the water is so firmly held by the soil particles that plant roots cannot uptake this water, and the plant begins to wilt. At this stage, even if the plant is kept in a saturated condition, it does not take up the water, and it is not alive again. So this point is termed as wilting point, and the percentage of water held by this water is called wilting coefficient. It represents 15 bar or 15 atmospheric pressure. Hygroscopic coefficient is the maximum amount of water that is absorbed by 100 gram of dry soil under the condition of 50% relative humidity and 15 degrees centigrade temperature. This is called hygroscopic coefficient, and the tension is almost 31 atmosphere or minus 31 bar under hygroscopic water. Now, available water is the water present between field capacity and wilting point. This is available water, and this water is beyond field capacity to saturation, where pressure is 0 atmosphere or 0 bar. The water is superfluous, that the water drains so quickly that plant cannot take it, or it is not available to plant. Or below 15 degree or below 15 bar, the water is so firmly held by the soil particles that plant cannot take up this water. The maximum water holding capacity is that point when it is the amount of moisture in a soil. It's all pores like macro and micro pores and are filled with water. It is a rough measure of the total pore space of soil, and the tension is 1 to 0 here. Now, moisture equivalent is a very important term frequently used in asked in question. It is defined as the percentage of water held by 1 centimeter thick moist soil when it has been subjected to a centrifugal force of 1000 G for half an hour. And it is defined as that field capacity equals to 0.86 into moisture equivalent plus 2.65 into wilting coefficient or wilting point. And wilting coefficient is also used to determine moisture equivalent. It is roughly wilting coefficient is moisture equivalent divided by 1.84. This formula are very important for solving any mathematical question in asked in GRF or SLF. Now these are some typical representation of the moisture class, soil moisture class, and tension along with pF value. pF is the logarithmic scale of water held like pH only. There a hydrogen ion concentration is considered here. The difference is only that height of water column is taken into consideration. For example, the maximum water holding capacity, the tension is in atmospheric pressure, that is almost zero, and gravitational water is less than 1/3, that is 0.33, sticky point 1/3 or plus almost 1/3, not 1/3. Field capacity is 1/3, moisture equivalent is 1/3 to 1, capillary water is 1/3 to 31, wilting point is -15, hygroscopic coefficient is 31, and hygroscopic water is 31 to 10,000 atmosphere. And water vapor, for water vapor we cannot determine the tension. Now the concept of soil moisture availability increases as the plant water content increases from hygroscopic point to the field capacity, beyond which again the soil water is not available because of all pores are saturated with water. Soil aeration is hampered, and root growth is hampered, as well as too much of soil water soil cannot hold. It leaches down so quickly that this cannot be taken up by the plant. So this is the range, field capacity, the wilting point. This is the range where soil water is mostly available. According to this, the plant availability of water, soil water has been classified in 3 biological scales, that is superfluous water, available water, and unavailable water. Superfluous water is gravitational water, available water is field capacity to wilting point, and unavailable water is hygroscopic coefficient and beyond that. Now, what are the factors that affect field capacity and permanent wilting point? Basically, for example, soil texture. Soil texture is the most important parameter impacting the field moisture, soil moisture constant, like field capacity, and what is called permanent wilting point. For example, the field capacity for sandy soil is very low, and clay soil is higher than for field capacity than sandy soil. Structure for well aggregated soil, field capacity is higher than compacted soil. Then soil organic, as we improve the soil organic matter, the field capacity also increases. And impeding layer, presence of any impeding layer, that is the any tough layer, that is rock layer or any other layer present in soil, will reduce the concentration of water at field capacity and also hamper the soil water availability to plant. And among that wilting point, the texture, for example, texture of the soil is also the most important parameter affecting the wilting coefficient of soil, that is permanent wilting point. For example, wilting coefficient increases with the fineness of the soil, that is clay soil has more wilting coefficient than sandy soil. And for type of clay, the type of clay present in the soil, that is kaolinite 2:1, clay like montmorillonite, or a 1:1 type of clay, that is some kaolinite, all interact and hampers the soil water content at wilting coefficient. For example, expanding type of clay retain more water, that is 2:1 clay retain more water than non-expanding type of clay like kaolinite, because expanding type of clays are usually smaller in size than a non-expanding type of clays, and expanding clays have internal as well as external surfaces, but non-expanding clay has only external surfaces for adsorption and of water. In that way, the type of clay also interfere the wilting coefficient and soil organic matter. As such, the organic matter content is increases, the content of water at wilting coefficient is also in higher, but the increase is very small. So it is to be noted that soil organic matter content increases the field water content and field capacity very high, in very high amount, whereas at the soil organic matter content cannot improve too much of water content in permanent wilting point. You can see here that the how texture is affecting the field capacity and permanent wilting point. Here it is superfluous water and it is field capacity line and it is permanent wilting point. As the texture increases from coarse to fine, you can see that initially field at very sandy soil has both low, that is FC and PWP both are low, so the gap the available water content is low. As we increase toward fineness, the silt loam soil, the distribution of sand silt clay is equal in equal amount, so the available water content is maximum because soil porosity, that is macro and micro pore, are evenly distributed and the highest amount of available water is achieved here. But in clay soil again, the water content does not increases so much in field capacity, so it hampers the you can see that the field capacity line is saturating here. So you can because of the that clay surface area is limited, and as it is as water occupies the surface area, the content it cannot increase further. So in that way, the water availability is highest in loam to silty loam soil. Now there are three concepts of soil water availability in basically. First concept is that first hypothesis assume that soil plant water activity, that plant water availability remains constant for among field capacity to wilting point, that is this line. No, in this range plant water availability is constant, that is water any amount of water present in this range will be available in equal strength or equal amount by plant. But it is not true, as the soil water content decreases gradually, the availability also decreases gradually. Then come the second hypothesis. It was proposed by Richards and Whiteley, and it stated that from field capacity, that soil water availability to plants actually decreases with decreasing in water availability after a certain point. That is, the water availability from field capacity to this point will remain same for the plant, but it will gradually decrease beyond this point. And third hypothesis, it is stated that plant water availability from field capacity to gradually decreases as the water content gradually decreases from field capacity to permanent wilting point. This three theory has been proposed for soil water availability concept. Anything to ask? If nothing is there, I will stop here and start my second topic. My second, sorry, I think I shared wrong screen. Now, my second topic is soil consistency and its importance. First, you have to understand what is soil consistency. Soil consistency, as I told earlier, also is the strength with which the solid soil materials are held together, or the resistance of the soils to deformation or rupture. It is measured in stickiness and plasticity. And soil consistency is also determined for wet, moist, and dry soil. This point should be noted. In case of wet soil, it is expressed as stickiness or plasticity, both. For example, soil consistency, wet soil consistency, we have to determine the stickiness, that is the ability of the soil particle to adhere to each other, and the plasticity also, that is the ability of the soil materials to change shape but not volume, and again under a constant pressure or force. And if we release that pressure, the original shape is obtained again. For example, you can see here the non-sticky soil. If the for wet soil, a small amount of wet soil is taken and is pressed between your first finger and thumb finger, that is, and then if it will be told non-sticky if no soil or practically no soil particles sticks on the figure like this. It falls from your hand. Slightly sticky will be told when it sticks to your one finger but does not stretch when the fingers are separated or opened. And it will be told sticky if it stretches slightly and then it breaks down. And it will be told very sticky if you stretch the your finger or separate your finger more, and the soil also touches your finger like this way. This was stickiness. And now for plasticity, we have to rub a small amount of soil within our palm and up to a wear of 3 millimeter thick, and it will be till non-plastic if no wear can be formed like this, and it will be till slightly plastic if it initially forms a wear, but it is broken when it is more pressure is applied. And it will be told plastic if the wear can be formed, but when it is broken and returned to its former state, it cannot be formed again like this. And very plastic if it is it forms where it retains its shape and it can again be molded to form a soil mold like initial shape, to provide it initial shape. For a moist soil consistency, we have to wet the soil by sprinkling water, just moistening the water. And moist soil consistency is defined by 6 terms. It is loose when the soil is non-consistent, a single grain structure like this. It does not form any soil mass. Very friable if soil crashes easily under a very gentle pressure but sticks together when it is pressed slightly. It will be told friable if the soil crashes under a gentle to moderate pressure. And it will be told firm if the soil crashes under moderate pressure but resistance is also felt from the soil. And very firm if the soil crashes under a strong pressure but it is difficult to do with thumb and forefinger. And extremely firm if you cannot crush the soil with your finger pressure. For dry soil consistency, we have to take a air dry soil and it will be loose if the soil structure is non-coherent, for example single grain structure, and soft if the soil is very weakly coherent and friable, breaking to powder or individual grains under a very slight pressure application, and slightly hard if the soil resists light pressure but broken when you apply pressure with your forefinger and thumb. It will be told hard if the soil resists moderate pressure and can barely be broken between the thumb and forefinger, but can be broken in the hands without difficulty, like by this way, by using your more force, by using more fingers. And very hard if you need more pressure using your all 5 fingers, and extremely hard if you cannot break your the soil mass using your hand. Now, the most important part of soil consistency is the Atterberg limit. For this, you have to consider a soil that has been soil mass that has been saturated and super saturated, better I should say, with water, and it is almost liquid state. In the so that is the soil, what so much of water has been applied that the soil water along with soil particle is flowing. In that state, the soil is in state of liquid state. Here it is mentioned. If we evaporate the soil, if the water and moisture content is reduced at the, and the moisture content will gradually reduce, and the point a point is reached when the soil water will come from liquid state to plastic state. That point is called flocculation limit of soil water. That is from liquid state to semi-liquid state. And then if we dry the soil further, it will again lose its water, and it will the water will evaporate gradually, and the soil water content will again reduce. In that way, soil will lose water, and a point will be reached when it represents there will be a migration from change of water from plastic state to semi-solid state. So in between, the solid soil will be in plastic state only. So it the liquid limit or upper plastic limit is the moisture content at which soil water changes from viscous fluid to a plastic body. And lower plastic limit is that point where soil changes from a plastic to semi-solid point. Soil water content will change. Soil changes from a plastic state to a semi-solid state, beyond which you cannot compress the soil, or that is the solid state of the soil. So 3 Atterberg limits: the flocculation limit, liquid limit, and lower plastic limit in soil. Now, shrinkage limit is that water content of soil below which soil ceases to shrink. That means this portion soil will not reduce its volume, so it will not shrink more even if you evaporate more amount of water. So plasticity index is that index, that is the difference in moisture content between upper plastic limit and lower plastic limits is called the plasticity index. Now another 2 consistency is provided. It is friable consistency or harsh consistency. The water content for friable consistency is permits easier crumbling of soil, and it is the best consistency for tillage operation. And harsh consistency is that consistency when upon dehydration soils become too hard due to clay cementation, and it requires more power to plow the soil at this water content, and soil becomes very cloddy, or clod formation takes place when you apply tillage operation or plowing. As I told earlier, the plasticity index is defined as water content lower plastic limit minus upper plastic limit. Now, what are the significance of this plastic limit? You can guess from the discussion that at liquid state soil will flow like water. So soil is not stable and it will flow under the pressure of water flow. So it is the soil erosion will take place. And the friable consistency is that consistency, soft or friable consistency is that consistency where crumbling of soil take place and granular structure formation takes place, which is optimum for plant growth. So tillage operation is done, should be done in friable consistency only. And these are the two important significance of soil consistency. Another part is left, that is soils crusting. The soil crust is basically a thin layer, maybe thick also, present on the surface of the soil, ranging in thickness 1 millimeter to more than 10 millimeter, and it has a bulk density more than the bulk soil, higher bulk density, that is 1.75 to 1.95 megagram per meter cube. And the silty soil are more prone to crust formation, and true sand does not form any crust in soil. How crust are formed in soil? For example, crust formation takes place due to the action of water as well as due to the action of soil, the radiation force of soil, radiation force of sun. What happens in crusting? First, what happened if a soil is directly exposed to someone has asked plasticity number, plasticity index is different or same thing? They are same thing. Now coming to crust, what happens here? You can see from the diagram that this is the intact soil without any for external forces. When water falls on the soil particles, it disintegrate the soil particles and disintegrate as well as disperse the soil particle, and form a thin layer which inhibits infiltration of soil water as well as soil aeration. And after that, when rapid drying takes place in soil, the surface tension force of the soil particle pulls dispersed particles, and a thin layer is formed on the soil, thin compact layer. You can see here all these pores has been filled by dispersed soil particles, which restricts the movement of soil water as well as air. This in that way the soil crust formation takes place. Here I have explained in detail that mechanical destruction of soil surface or aggregates takes place by raindrop impact, then leaching of fine particles, and the subsequent deposition takes place in the underlying pores, that is washing in, that the disintegrated soil particle is washed down the soil pores. Next, what happened? The compaction of soil surface to form a thin layer, which restricts the further entry of water and air. Then cementation takes place due to rapid drying of the soil due to sun radiation, and then the crust are formed. Some crust are formed by translocation of this disintegrated soil particle to other soil places. They are called translocational translocational or depositional crust. Soil crust can be defined or differentiated in three types, that is slaking structural crust and erosional depositional crust and cryptogamic crust, that is biogenic crust also called. What is slaking crust? Slaking crust are usually formed due to disintegration of a sodic and weakly aggregated soils by the impact of raindrops. Its thickness is only 1 millimeter to 5 millimeter. As it is a sodic soil, already the soil structure is broken, and so textural separation between coarse particle and fine particle cannot be noticed here. And another type is infiltrating crust. This type of crusting takes place in loam soil or medium texture soil, which in which the raindrop erodes the soil particle and top soil aggregates, and causing separation of sill particles and sealing of void space by leaching down the smaller particles. And in that way, a textural separation could be seen in infiltrating crust. And for coalescing crust takes place when wet soil is crust formation takes place in wet soil. This is a very thick crust, up to 20 millimeter crust formation takes place. And sieving crust are formed by the impact of raindrops on sandy soils, where aggregates are extremely fragile and leading to sorting of soil particle, causing concentration of the coarser particles at the top layer and finer particles at the deeper layer. So a typical textural separation is there in sieving crust also. Someone has asked a question that why crusting is more prone in silty texture rather than clay texture. It is because that clay soil are very active, clay particles are very active, and they when stick, the force required to disperse or disintegrate the clay particles are much higher than that of silt particle, and clay particles are not freely available in soil. They are so active that they form the complexes with sesqui oxide like iron and aluminum oxide. In that way, their stability is increased in soil. So so the force required is much higher in clay soil than silty soil. In that case, that's why the crusting is more prone in silty soil than clay soil. Erosion and depositional crust is that if soil particles are eroded from this place, a hard subsurface layer will be exposed on the top, and that hard subsurface layer will come to the top, and it will not allow plant to germinate and water to infiltrate. In that way, crust formation, erosional crust formation takes place. And depositional crust is if these soil particles will be translocated by water and deposited in some places, and they will seal the pores to another places and form a thin layer of finer particles or disintegrated particles, causing impedance for root germination, root growth, plant germination, and soil aeration. And cryptogamic crust is the crust that is basically the biological crust, or it is also known as good soil crust. This is made of algae, fungi, lichen, mosses, bacteria, or any other biological material. As these are biological material, they decompose and they supply nutrients to plants. So this is a good crust, and for this reason, cryptogamic crust is often not considered as soil crust. Now, soil properties that is related to crust formation. First is soil texture. As I told earlier, that medium textured soil are usually very susceptible to crust formation. whereas silty soil, clay soil or porous fragments seem to protect smaller surface aggregates from raindrop impact. And clay mineralogy, generally if the dominant clay mineral in the clay fraction is carinate, crusting is less, whereas if the clay is smectite, elite and micaceous, they are more prone to crusting. And organic matter content, as organic matter, higher the organic matter content, the stability of the aggregate, as we studied in yesterday's class, that organic matter content increases the aggregate stability. So the stability of the aggregate increases, so the organic matter content will reduce the crusting tendency of soil. Sesqui oxide content, the stabilizing effect of iron and aluminum oxides are commonly regarded as an important factor in aggregate formation also, because they are cementing agent. So they reduce the crusting. And exchangeable cations, if the soil is saturated with sodium type of cations, it will be more prone to crusting, whereas coagulating cations like calcium, iron, aluminum will reduce soil crusting. And soil water content is also an important factor for crusting. Now, how soil crusting can be controlled? As you understand the factor of crusting, first is what is the first factor? That is raindrop. So we have to reduce raindrop impact. How can we do that? By surface mulch, simply. And then addition of organic matter, addition of artificial soil conditioner by to increase the aggregate stability. And in sodic soil, lowering of exchangeable cations, exchangeable sodium by enhancing gypsum and pyrites, it will also reduce crusting. And a light tillage in moist soil will break the crust before it hardens. So light tillage is required for crust breaking. Now, how we measure soil crusting in lab? For that, we have to form a soil briquette like this, which has a definite length, width, and breadth, and we place the soil bricks under a force. This through this machine, we are applying force on the soil briquette, and we can measure the force digitally. How much force is required to break the soil briquette, and that force is converted. That force is measured as soil crusting strength or soil strength, and it is measured as 3 FL by 2 BD square. That is this is the force and deflection. That is, force is increasing, and in this point the soil briquette breaks and forms. Thereafter the force decreases. In that way, we can measure the soil crusting. Okay, anything to ask in this section? If not, I have only this much to teach today.
Hello. Okay, sir.
Yes.
Completed, sir. There is
Okay, there is no more questions. If there is any question, please ask to our expert.
If any question arises in the later part of the students in mind during study, they can share question with Sumon. I can answer in written form also, no issue.
I think there was no question, sir. On behalf of the organizers, course director, I am very thankful to Dr. Avijit Ghosh, sir, for giving a very nice lecture regarding the soil consistency, soil water environment, while whereas the soil environment and everything in normal soil as well as the saline and the sodic soil, all the plastic limits and all these things. He has explained very nicely. I am very thankful to Avijit Ghosh, sir, for giving a very informative lecture. Definitely this lecture will be very helpful and resourceful for the students for preparation of the JRF, SRF, as well as the ARS examinations. Thank you very much, sir.
Thank you, sir. Thank you.
Thank you.
Abhijit sir. Hello, Abhijit sir.
Hello. I am
Yes, sir.
listening. Tell. I am listening.
Yes, सर चूंकि अपने पास थोड़ा सा टाइम है सर, मैं इसका मतलब ये बेनिफिट्स लेते हुए मैं सर आपसे मतलब एक क्वेश्चन है मेरा एआरएस से रिलेटेड कि
हाँ,
जो
बताइए।
बच्चे एआरएस और एसआरएफ तैयारी करते हैं
हाँ।
उनको किस तरह के बुक पढ़ने चाहिए और कैसे पढ़ने चाहिए, इस थोड़ा सा सर मतलब इलेबोरेट करो इस चीज को।
Actually, for ARS
क्या होता है,
preparation.
सब पढ़ते तो हैं ही सर।
Okay. I'll tell in detail. Now, you can note down the name of the books, and I will also supply the name of the books during as I supply the study material. For ARS, there are 6 units in ARS. First one is soil pedology. For that part, you need to study the book of J.S. Sehgal, a textbook of pedology by Dr. J.S. Sehgal. Second is soil physics. For that purpose, you need to study the book of by our society, that is Indian Society of Soil Science book, that is the old one that came in green cover page, and Fundamentals of Soil Science, that was the name is Fundamentals of Soil Science. And another book is for soil physics is Dr. A.K. Shah by the name of the book is, I can tell, Textbook of Soil Physics by Dr. Arun Kumar Shah. And for soil chemistry part, you need to study our again that Fundamental of Soil Science book, as well as one more book is required for studying soil chemistry, that is I forgot the name of the book. The author name is Kim H. Tan. Kim H. Tan. You can write someone. Kim, K-I-M, Kim H. Tan, T-A-N, Tan. These two book are very important for ARS writing, question answer writing. And for soil fertility, first you have to read Fundamentals of Soil Science, and then Tisdale and Nelson. One book comes from the author Tisdale and Nelson. Tisdale and Nelson.
Soil fertility and fertilizer.
Soil fertility and fertilizers, like that name is there. And for soil biology, again you have to read that Fundamentals of Soil Science and the book by Mark S. Coyne, Introductory Microbiology, Introduction to Soil Microbiology. Mark S. Coyne. Mark S. Coyne. Coyne is spelling C-O-Y-N-E. Mark S. Coyne. And anything I forgot? Statistics. For statistics, you can, based upon the syllabus, you can constant Rangoswamy book. One book is there by S. Rangoswamy. And for preparation of
how to prepare.
Yes, I am telling that. ARS exam has three stages, that is prelims, mains, and interview. For prelims, you have to you are asked some multiple type of question. You have to just tick mark. For this, you need to go through all this textbook and note down the important points on your copy and revise it as and when you get time. For mains part, I will mainly emphasize on writing part. Practice as much writing as you can, because in main parts you have to write 240 marks answer within 180 minutes. So time is it is felt that time is the most limiting factor there. So you have to manage that part mostly. For that part, you have to prepare. You have to read 1 or 2 unit, or first you have to read 2 to 3 chapter. Then prepare some question, 5 marks question by yourself only. Like you read the chapter of soil physical properties. Now you made a question that factors affect. What are the factors that affect soil ball density? Now you try, likewise you can make 10-20 question in your one page, and uh, sit down to write it within each question by 5 minutes. Then only you can complete your whole uh, question answer part in exam also. Similarly, for other part and other chapters also, you have to exercise by writing. Writing is the most important exercise in ARS mains. And after you qualify for ARS mains and for ARS interview, you should read your textbook very thoroughly, and also some data fact, present agriculture production scenario. What is the present agriculture problem that appears in the newspaper, daily newspaper you have to read. What are the policy government is implementing and government is proposing? What are the MSP government is announcing? Like that, every recent data as well as your knowledge on subject, both should be at your mouth tips. In that way, you have to prepare. Anything more to ask about that?
Sir, what ought to be do for sir SRF sir? How to get some best rank in SRF sir, or why to prepare for object MCQ type question sir?
In JRF now, MCQ type of question is not
Approach
there.
toward the solving the MCQ type questions sir.
I think in JRF, the MCQ type of question has been removed, and it is mostly assertion and descriptive assertion type of question. That is cause effect question.
Yes sir, yes sir. For the sir,
Huh? Yes. Hello.
yes sir.
For that, you have to.
Yes sir, you are right sir. Essentially that region type question is more asking.
For that, you have to study your textbook more and more. In that, after studying your textbook, you need to solve, and group study is one of the most important thing in SRF and JRF. As well as in SRF, some general awareness question is also there, asked in first 20 question, a general awareness question. For that, you again need to read those newspaper, policy, what schemes government are launching and what are the schemes ongoing, all these things. And for subject, that is in soil science, agronomy and soil science, both questions are asked. For agronomy, you need to read one crop science book, crop production technology book, that is Chidda Singh and Reddy and S.R. Reddy. Two books are there for fundamentals of agronomy, knowing the fundamental properties of agronomy. Basically, those things are only asked in JRF. So, in those books, you have to also read for getting best rank in JRF in natural resource management too, because it is not conducted in SRF as soil science and agronomy. It is conducted as natural resource management too. In that way, so you have to cover your whole syllabus first, not only soil science. Agronomy you have to study also for this purpose.
For for sake of information of the student, that we are very fortunate that with us, Dr. Avijit Ghosh sir, who secured first rank in JRF, first rank in SRF, as well as second rank in ARS examinations, as well as that he has first rank for the PhD examinations. That means he studied very hard and he has given very good points for you. So accordingly, you refer all these books. Thank you very much, sir, for giving very nice and very informative information, sir.
Thank you, sir. Thank you very much.
Thank you, sir. Once again, on behalf of all students, faculty, I'm very thankful for you for sparing your valuable time for the students, sir. Thank you, sir.
Okay, thank you.
Okay, Suman Kumar, if there is no question, please end the meeting.
Okay, sir. I end the meeting, sir. There is a
Yes, please.
question.
Okay, you end the meeting. Suman Kumar.
Yes, yes. Yes, sir. My side it's ended, sir. But it's not ended. Who is host?
Okay, okay.